My name's Thomas Holt Ronzi. I'm the senior applications engineer for the Northeast. So I'm your technical liaison if you're a dealer in the Northeast. I answer questions about how it works and what the best Q-SYS solution is to get your project done. I'm joined today by Dan Waltons. He's our national training manager. He handles all of our training initiatives as well as all of our webinar initiatives, and he's in charge of the experience centers. So he helps make sure that when you guys go out to Austin or Costa Mesa or soon New York, that you have the best experience possible and that you get really good high quality training from all of us. So he's going to be handling Q&A today, and we're going to talk about best practices and gain structure. Yes. Chip asked if am I a good first contact for interesting technical support questions? So the answer to that is actually no. So I handle everything up pre-commissioning. So once your project is commissioned and you have customer sign-off, typically the best and fastest way is going to be to contact Q-SYS support. First and foremost, it's because their hold time is less than 5 minutes. Whereas if you shoot me an email or give me a phone call, depending on what I'm doing at any given point in time, I'm usually 12 to 24 hours response time. So I'm for asking questions about how you want to program something, or I'm trying to solve a design question. If they're interesting pre-sales questions, absolutely hit me with them. If you're on site and you're in a jam, contact Q-SYS support. They may still loop me in if it's like a programming question or something that I can help with. But that's where the divide happens. If you're in a bind, call support. All right, let's jump right into to one of the things you will be doing on site, which is tuning your gain structure for AEC and Q-SYS in general. So this class is not meant to teach you how to be a live sound engineer. It's not meant to be the end all and be all of gain structure. There's a lot of places you can find this information. My personal favorite is the Yamaha Professional Sound Reinforcement Handbook. It's a ancient tome of live sound knowledge if you need that. But this is specifically meant to give you a better understanding of how gain structure works inside of Q-SYS and how to get the best out of the AEC that we made. Like everything else in gain structure, garbage in is garbage out. So you have to start with a good signal flow, good gain structure on the front end of your system if you want to get the best out of it when it hits the amplifiers or that USB signal on the far end to go to your compute unit. This image we're looking at here is, this is a typical signal flow for a fairly robust, conference room or small lecture space. We've got a bunch of mic line inputs on the left that we'll be connecting microphones to. We've got some signal conditioning in the middle, so high pass, parametric, low pass. We've got some user level controls for those program feeds. And then we've got some auto mixing, matrix mixing to break those signals out where we need them to go. And then some output conditioning to make sure that those amplifiers are tuned properly and we're protecting the speakers. And then output to the far end. What this doesn't show is it doesn't yet show your AEC. It doesn't show your speakerphone or VoIP connections. We'll add those in a little bit later, but this is kind of home base for us, what we're going to do for the next hour. So before we dig too deep into Q-SYS though, let's set the stage a little bit and talk about some terminology. So some of this will probably be very familiar to you. Some you may have never heard before, but on the right, we have a chart that shows, this actually shows the high sensitivity and the low sensitivity for a Q-SYS preamp. So if you plug a mic line into a Core 24 or into a QIO ML4i, this information will be highly relevant to you. So the first one at the bottom there, that minus 81 dBu, that's what we call the noise floor. So anytime you you flip the switch on a preamp or an audio interface, or you turn on that Q-SYS core and you bring that signal into Q-SYS, you are energizing that circuit with electricity. And so because there's constant voltage flowing through that circuit, there's a little bit of noise floor that gets introduced. That's true of any preamp, any audio interface, um, anything that you are touching with electricity and you want to get sound out of it, there's going to be a noise floor. Depending on how much money you spend on that circuit will depend on how loud that noise floor is. So for Q-SYS, it's minus 81 dBu. So dBu is a base 10 logarithmic standard for referencing how loud a signal is compared to something else. In this case, it's compared to a reference voltage. So dBu references 0.775 volts. So if you take minus 81 dBu and multiply it by 0.775, you get a specific number that you can use to correlate to how loud that signal is. But usually when we're talking about sound, we use dBu or dB. dB itself, so in the middle there, that dynamic range. So dB is a logarithmic relational term. So whenever you see dB and you don't see a unit at the back of it, either U, A, DBC, whatever extra number letter at the back of that, if you just see dB, that means that this is a relational value. So this middle number, the greater than 105 dB, this is what we call our dynamic range. So this is how much signal we have to work with between the maximum value and the minimum value of our circuit. And that maximum value, which is right up at the top there, that plus 24 dBu, that's what we call the clipping point. So that's the maximum voltage that we can apply to that circuit before we actually exceed the capabilities of the preamp circuit itself. This is called clipping. In the analog domain, it's analog clipping. In the digital domain, it's digital clipping. We'll talk about that. I'll talk about that in a moment and what the difference is. But this dynamic range is a very important thing to keep an eye on because it's the maximum range that you have to work with. And as we start to tune the system, that becomes really important, and that's the magic number you want to keep an eye on. So this slide, we've taken that same chart and we've broken it down into additional steps. So we still, on the right here, if I can grab my pen, we still have our dynamic range, this maximum number, this 105 dB, but now we've broken it into a couple different segments. So that top 20 dB, that's what we call our headroom. So when we've got this signal set up properly, we should have in Q-SYS about 20 dBu of headroom that gives us room to increase that volume, move that signal around to make sure it's loud enough to be heard inside the room. We like 20 dB. Doesn't have to be 20 dB. If you go to a concert venue, a lot of times they're using that headroom to make sure that you can hear the bass or the guitar properly. But in a conference room, we want to start with a flat mix, and we want to move that based on what we need to do to get levels up to where they have to be. So that's our headroom. 20 dB is where we want to start. When you're working with SPL, 10 dB is perceptively twice as loud. So if you move that signal up 10 dB and you're left with 10 dB of headroom, you've made it twice as loud. So again, dB is logarithmic. So as that changes and goes up further, that perceived loudness gets even higher. So that's just a thing to keep an eye on. At the bottom here, this SNR, so this 85 dBu, this is what we call our signal to noise ratio. So this is the difference between your nominal level and your noise floor. So this is how much room below your sweet spot that you want to have. So this is all the room below. So the higher this number is, the cleaner the signal is, and the more room for AEC and other processing you have to operate in. So generally, we want this number to be as high as possible while still leaving us 20 dB of headroom. And in the middle here, this plus 4 dBu, this is our nominal level inside of Q-SYS. So when we start everything, if you bring in that preamp and you gain it up to plus 4 dBu, you've not put any digital gain on it. This is what we call nominal level. So there's 20 dB of headroom. We've got 85 dB of signal to noise ratio before our noise floor. That means we're ready to go and we're ready to continue tuning the room. And now I have to clear all of these markups. There we go. So everything we just talked about with signal floor, nominal level, clipping, all of that was happening in the input device in the analog domain. So that was all happening here. So on this chart, input device is your physical microphone. The connection, this arrow is the connection between those two via that mic cable or that mic cable, the Phoenix connector. Inside the analog preamp, that's where we're going to dial in our nominal level, make sure we have our signal set up properly to get the best signal to noise ratio out of that. Then it's going to go inside of Q-SYS to what's called an analog to digital converter, or an ADC. And this is where we take that voltage, that dBu voltage that we were talking about, and we convert that to ones and zeros, or to bits. This happens instantaneously or near instantaneously, and it happens by taking each voltage waveform and converting it to an amplitude as well as a frequency. And when you see things like sample rate and bit depth, these are parameters for the analog to digital conversion. So if you see 48 kilohertz sampling rate, that means that it's sampling at 48,000 times per second, and you get a usable frequency range of 0 to 24,000 hertz, or 0 to 24 kilohertz. That rule of thumb is actually called the Nyquist frequency. So it's 1/2 of your sampling rate is your usable frequency. I just like to add that as extra information for you guys. But so generally, whatever number you see on the box for the preamp or the console you're working with, or the Q-SYS core, whatever DSP you're working with, if it has an A to D conversion, it says 96K. Okay, cool. I have 48,000 hertz of usable frequency range with your bit depth. So Q-SYS is 48K24. So that means we have 24 bits of amplitude depth. So that waveform, based on how wide it is, we assign a loudness value to that in floating point. That's called our amplitude. So when we digitize that signal, we know roughly how loud it is, and we know how to handle that in the digital domain. Everything past this point is in the digital domain, and we start to refer to it in different terms. So inside the digital domain, we refer to it, instead of dBu, now we use DBFS, or dB full scale. So decibel full scale has a different set of parameters for that clipping point, that noise floor, and the dynamic range. So if you open up a Q-SYS gain component, you'll see that they go from plus 20 to minus 100. So, but they always start at 0. So 0 dBFS is our clipping point, because everything beyond 0, we're digitally amplifying that signal. We can't really add any more real world data to that. We're adding things artificially. So 0 dB is your top level. Minus 100 is your noise floor. Minus 100 dBFS means no signal, absolutely nothing. So minus 100 is you turned off the digital spigot, you set all the digital bits to 0, and you move through. So by default, Q-SYS gives you 20 dB of headroom in the digital domain. That's just how it's configured. Everything is set up properly that way. We don't really have to deal with anything extra. When we're looking at this inside of Q-SYS, so over here on my mic line in block that we've set up, we've got a peak level here. So that's peak level in dB full scale. So we don't show you the analog metering inside of Q-SYS. And the reason for this is the way you meter signal inside of a DSP is you actually have an extra part of your analog circuit where you take voltage off of that microphone prior to the preamp or after the preamp prior to the analog to digital conversion, and you run it through a resistor chain so that you can measure how much voltage is in the system. The thing about that is when you do that measurement, you actually take some voltage away from what the preamp and the analog to digital conversion are doing. So this was a decision by our engineers way back when we built the first Core 110, that we didn't want to sacrifice any of that voltage on the preamp side. So we just did all of the metering on the digital side. Once it's been digitized, we measure everything from there. So that's why Q-SYS doesn't have any analog metering on the input side. On the output side, we do have analog metering because we know exactly how much voltage we're sending out to the outbound system, so we can just parallel that off and do that. So you'll see this peak input level in DBFS. You're always looking for minus 20 DBFS. That's your nominal sweet spot. So when you're turning that preamp gain, you're going to see this adjust as well. Underneath that, you've got your preamp sensitivity, which shows in dBu. You also have a preamp gain knob, which shows you how many dB of gain that you are applying relationally between DBFS and dBu. So we do this for every single input, get everything tuned up to nominal, and the system is ready now to mix. With microphones in general, again, just looking for that 20 dB of headroom. Doesn't matter how loud or soft. Ideally we want to have that 20 dB of headroom on the analog side, because if we mess that up, if we make it too loud and as we increase that gain, you're going to reduce that signal to noise ratio, and it's going to get smaller and smaller and smaller because we're bringing the floor up to meet that maximum level. So as little gain as we need to reach 20 dB of headroom, we can always add more in the digital domain because that's sampled data. And before anybody asks, yes, that does introduce noise because you're artificially adding gain to a system, but you can't fix signal to noise ratio inside of DSP. You can only make the signal louder by just increasing the amplitude of the signal digitally. So AEC requires a minimum of 20 dB of SNR. I think inside this document, we actually say 15, but I personally like to have 20 dB of signal to noise ratio. Actually, we say 35 because it's on the next slide. So 15 dB is the minimum, absolute minimum of signal to noise ratio that we have to have. So this signal here is minus 31.4 dBFS, which is not enough intelligibility for the AEC to work properly. We decrease the gain. Now the noise floor moves down, and now we have enough for intelligibility. Again, we can always increase that volume digitally, but it's very difficult to make a noisy signal sound good. And in fact, most of the time you won't be able to get there. So that's analog gain staging. That's just as quick as possible analog gain staging. We have a lot of stuff to cover, so I'm going to keep moving forward. Now we're into equalization. So typical EQ path is a high pass filter, which takes everything above a specific frequency and passes it through. Everything below that frequency, we cut it off and get rid of it. So typically we set this around 60 to 80 hertz to start. For microphones, I like to go as high as 115, 120 hertz for just, a handheld microphone. Ceiling microphones, because there's a lot more air around that microphone. It's up in the ceiling, so it might be also catching information from the ceiling moving around and vibrating. that stuff can, I might go as high as 200 hertz. Um, uh, you know, there's a couple different slope options to choose with the high pass filter, but doesn't really matter. The default is fine for most cases, unless you're going for something specific. Most of the time, it's fine. Parametric EQ. This is customizable EQ settings. So high pass and a low pass have a fixed curve depending on which slope you select. Parametric has a width or a Q factor that you can actually change to widen or narrow the cut or boost. Typically, we want to use this only to reduce feedback. So finding specific feedback frequencies, cutting those out, and moving on. Don't try and use it to add color. It's not a studio EQ filter. That's generally reserved for specific equipment. Q-SYS can do some of that musicality, but it's not designed for it, and it's not particularly good at it. It's particularly good at being a functional utility for making your signal path clean. So, and the last one here is the low pass filter. So, in the same way that the high pass filter passes everything above a specific frequency, low pass filter cuts everything above a specific frequency. And passes everything below that. So we start around 16 kilohertz because Q-SYS, the maximum is 20 to 24 kilohertz, but that's a lot of information that doesn't tell you a whole lot about intelligibility. 16 kilohertz is a good starting spot. You can go as low as 8 before you start to significantly impact human speech. And talk to the mic manufacturer. A lot of them still have frequency response curves, which show you how sensitive the microphone is to specific frequencies. A good place to start if you want to just flatten everything out is you can actually take that curve and you can just invert it in your parametric EQ, and that will flatten out the microphone. This doesn't always sound particularly good, but if you know that a microphone, for instance, 1.4 kilohertz is a particularly common feedback frequency in voice lift systems. So if that microphone is boosting 1400 hertz, then maybe you want to cut some of that out to reduce how much feedback is going to be in the system. Now, you want to be careful about that because there are specific speech frequencies that we want to be aware of. So 250 to 1000 hertz is where all your vowels are. This is also where a lot of the body and resonance from the human body comes from, because it's actually your chest that you're hearing. So you're hearing, chest, stomach, a lot of that meat and bones inside your body is resonating, and that's providing the character of your voice. That helps, so that people know the difference between me and Dan. If we, flip those, Dan's a larger guy than I am, just a little bit.
I have a more resonant cavity.
Yes, exactly.
But also,
Whereas, oh,
that's
go ahead.
also why your white and pink noise blends for sound masking are typically in that range, because the idea of sound masking, completely off topic here on a gain structure, is to reduce the intelligibility of the vowels, so you're not hearing what someone's saying, it's just noise. So people
Yes.
always think it's a magic sound sucker. It's like, no.
Nope,
Anyway,
it's the inverse actually from a sound sucker. It's
yeah.
flooding your ears with information that distracts from these specific frequencies. So 1500 to 6 kilohertz is where all your consonants live. This is where a lot of the head of your the head noise. So if somebody's got a particularly nasally voice like myself, that this is where they are going to be more emphasized. So you want to be careful about cutting anything out of these frequencies unless you absolutely have to. This is where this is where a lot of the character of somebody's voice is. Actually, okay. I'm gonna pause for a moment because we have a really good question. Do we always want to have the components in that order? High pass, parametric, low pass? And the answer is no. It depends. So, and that's if you talk to guys like myself who have a lot of sound experience or a background in live sound or studio work, you'll find that the answer to a lot of these questions is it depends on what you're trying to accomplish. So in the case of Q-SYS, we like to do this high pass parametric low pass as a best practice because high pass cleans up all of your low end frequencies. The parametric removes a lot of the middle frequencies, and then the low pass gets rid of all the extra data up at the top end. Once upon a time, way back in the day, there was a specific reason why you would do all of it in this order. You would do your high pass and your low pass before your parametric because the analog equalization equipment was not as good as it is now. So you physically wanted to remove extra data so that that EQ that was running on vacuum tubes was actually able to drive more efficiently. This doesn't really matter in the digital DSP world. I know I just said digital and digital twice, but the digital signal processing world doesn't really care as much. It's what you're trying to accomplish with it. If it serves your purposes to have the high pass and low pass in front of the parametric, or it just helps, set the stage for you a little better, go with that. One thing to note is if you put your parametric at the front and you may find and work left to right as a lot of us do, you may find that you're cutting frequencies that would be isolated by your high pass and your low pass filter anyway. So you may end up pulling out of 80 or 90 hertz because you've got those bypassed and you're hearing more low end and high ends than you want to, and then you'll turn on the high pass filter and you won't hear a difference because your parametric is cutting those frequencies already, and now you've used up your parametric band. Um,
I've
it's
also I've also had a couple of audio, gurus, good people with good ears and things like that that said our parametrics are really pretty efficient. And one of the gentlemen said, I've moved to just putting a 5 band parametric in or a 7. First band is for high pass and the last one's for low pass, and I have 3 to 5
just using
notches in there to do what
the
I want to
shelving
do. Yeah, yeah,
functions in
just kind of
there.
that way. So, I always I think you hinted to this. It's like artwork, right? If we say draw a car, not everybody's going to draw a 1978 Toyota Celica, right? But kind of understand that. So yeah.
Yeah. The analogy that I was taught, again, way back in the day, is that post your gain staging, you have your giant slab of marble, the giant rectangle of marble that they cart into the art studio, and all of these equalization, compression, dynamic tools that we're going to talk about over the next couple slides. All of these are the various pieces in your tool belt that you can take to chip off and remove pieces to eventually end up with David. As that's the goal for all of us, is to end up with a beautiful marble sculpture at the end of it that lives in perpetuity. Depending on the complexity of the room, you don't get there. But each one of these tools is designed for a specific thing. And I don't necessarily want to use the parametric to try and, lop off large chunks of my signal. It's pretty good at it with the high and low shelf functions, but they can be accomplished more efficiently with a high pass filter. The last speech frequencies are the sibilants. Insert S&L joke here. This to S, T, and Z happen between 5 and 8 kilohertz. This is where the bulk of your intelligibility is going to come from as well, because the way our ears work, we kind of use the consonants and sibilants of speech to our brain kind of skips the stuff in the middle and we auto complete stuff for us. So if you cut from here or you cut too much out of the consonants, you will directly harm your signal intelligibility, and your STI measurements will suffer from that. So just be aware of it. A lot of people do want to still cut from this area or put, like dynamics on this area in the studio because S, T, and Z sound pretty harsh on a microphone and they're very sensitive a lot of times. So if it's a really punchy system, then these might want to still come down just a little bit. So once you've completed your parametric and you're in the process actually right now, but you don't have a lot of time to deal with actually going through and doing this all using the good old Mark I hearing tools, your ears. Um, there is a tool built into Q-SYS for this. It's called the notch feedback controller. Some of the live sound guys in here are probably groaning because they've heard of something like this before that you used to be able to put on top of your mixing desk. You put it inserted on a channel. It's called a feedback destroyer. It does basically the same thing. A notch feedback controller listens to specific frequencies, listens to how loud those frequencies are, and when they exceed a certain amplitude, it cuts them. It uses a notch filter to cut them, which is why it's called the notch feedback controller. It uses notch filters to kill feedback. So the way it works, you open it up typically, you'll set a threshold, which is the dotted line that goes across the x-axis. And then you will set a minimum dynamic frequency, which is the leftmost y-axis dotted line, and a maximum dynamic frequency, which you can't see here because it's set to 20K, which is the maximum that the graph shows. And that creates a window. So everything here in this upper right quadrant, that's the frequencies that can be cut by the notch feedback controller. So this system has 4 dynamic filters that can be used. Those 4 are currently active right now, which means that it can't add any more filters. So the way you typically use it and the way we recommend to use it is you turn it on, you set it up, you start talking into the microphone. As it fills up these filters, you add these frequencies. If you hover over one of these carets, it'll actually tell you the frequency and it'll tell you how loud it was. You cut that with your parametric EQ. So instead of taking 12 dB, which is what the notch feedback controller is doing, you take maybe 4 to 6 dB. Then you clear out the notch feedback controller and you test again. And you just repeat this process, attenuating those frequencies until your feedback is done. Ideally, you want the system tuned out so that somebody can get really into the microphone and it's not going to ring out, but not so far that the room sounds dead. If you take a parametric, widen it up and set it in the middle and just hit the gain all the way down to -20, you'll hear what this sounds like in the room or over headphones. It sounds really dead if you just start lopping off frequencies whole cloth. So just a little bit goes a long way to reducing the sensitivity of that signal to feedback. Once we've gone through that process, remove the feedback controller. So the notch feedback controller is constantly doing what's called a fast Fourier transform. Without getting into it, it's a process of converting digital signal to understanding digital signal as that scaled graph. It's really processor intensive. So if you leave a bunch of notch feedback controllers or put a bunch of them on every channel, you will eat up a lot of the processing in your core that is reserved that we want to save for things like automatic mic mixing or AEC or Lua scripting. You'll just eat up a lot of that processing that you want to use for other things. So once you're done with the notch feedback controller, typically you take all of them out. If you want to leave one in for, the money channel, if you've got, a lav mic that the CEO talks on stage on, and you want to just have it in there for safety purposes, then you just bypass it until he goes on stage. Maybe you turn it on so that you get a little bit of a live feedback attendant, but try to limit the use of the notch feedback controller if you can. Then we have to take it into our mixing stage, and we actually take this signal, we combine it with all the other signals, send it to specific zones, or mix those down to a single channel if we're doing auto mixing. So the 2 major types, matrix mixer, which is take a signal and send it to any one of a number of outputs, or send multiple signals to the same output. This is user defined, so you get to decide where those signals go, and the output level can be mixed either at the cross point level or the output of the actual output channel out. Automatic mic mixers are designed to do basically the same thing, but they don't require an operator. So the mics are automatically mixed to either each output or a single mix channel. Q-SYS allows you to get both of them as well, so you can have the individual channels post auto mix as well as just a single mix channel. Typically, we just use the mix channel. It's just more convenient for you because you're already summing all those signals. And there's two ways to decide how you want to do that auto mixing. Now, before I go further, Steve asked, is it not advised to use a notch feedback controller on an output? So yes, generally speaking, don't use the notch feedback controller on an output. The main reason for this is that when you're using it on an output, you're set typically like in the case of what Steve's talking about, you would be putting it on the output signal to a speaker that's over your head for live sound reinforcement. This notch feedback controller is going to attenuate all signals going to that speaker. The reason this is typically bad is if you have a bunch of mic signals coming in and you have program signals that are also being fed out of that same speaker, then you're going to really change the character and color and tone of those program audio signals, which they're not really meant to be EQ'd or messed with dynamically. They're meant to be post-processed signals like YouTube videos or stuff like that you should just be playing back as is. And you're going to be dramatically impacting everything without regard for whether that's actual feedback or if, I don't know, maybe you're watching it's the training center at your dealer's office, and you're talking about signal generators. If you have a notch feedback controller on that system and the playback system plays a 1 kilohertz tone, I don't know, maybe you're listening to an old BBC recording and they've got the pips in there. Those will set off the notch feedback controller, and now if you're using a dynamic, it'll be for 5, 10, 30 seconds. If it's a fixed filter, that's there until you go back in and manually clear the system. You now have a 12 dB cut at 1 kilohertz, which is going to demolish your signal. So if that's only on the microphone, on the signal input side, then it's only pulling that 1 kilohertz out of that specific mic that reacted to the feedback. So that's generally why you want to have it on the input side, not the output. So looking at matrix mixers, first we have a crosspoint mixer. So this is the typical mixer that you're going to use. This is the matrix mixer that you just grab out of Q-SYS. So by default, it has along the bottom, we have input faders. So all of your vertical channels are the inputs that you bring in on the left-hand side. The horizontal channels are your output channels. And in the middle at the intersection of each of those, you have a gain. So usually when you're doing mix minus or traditional crosspoint mixing inside of Q-SYS, these values are either going to be 0 or negative 100. If you're feeding them to something like a lecture system and you just find that that specific output is too hot, you can either pull down the input crosspoint gains. So maybe you do a 10 dB reduction just on that individual input, or you can take the output gain and reduce it by 10, 20, 50 dB, whatever you need to do. You can actually modify these. So maybe a specific specific input is really loud. You can handle all of that. You can also set these up so that they have crosspoint mutes. So you can mute an individual input going to an individual output without setting up that gain. There's a lot of capability in here. But let's talk about auto mixers. So there are two types of auto mixers inside of Q-SYS. The first one and the most common one that you're going to use is the gating automatic mic mixer. So this is what you would put on ceiling mics or console dais mics. This is when you need to remove a signal entirely when it's not being used. A lot of times this is the conferencing and speech reinforcement desired functionality. This uses what we call an adaptive threshold for that gating, where basically instead of saying any value that is above a certain level, which is how a normal noise gate works, it says I'm going to look at all of the signals that are coming into the auto mixer. And when one signal is louder than the average noise floor of the entire set of channels, then I'm going to open the gate for that mic. So that's what we mean when you see signal level above noise uh, on your chart. That's signal level above the averaged noise floor inside the auto mixer. Um, there's a bunch of other settings in here. The most important one is on the right. It's the max nom, or number of mics. Typically for Q-SYS, for Q-SYS AEC and conferencing, we recommend 1 to 3. You can open this up if you need more, but the more microphones you add into the system, the more gain attenuation happens. So the way that auto mixers are designed to work is they have a target of 0 dB, of 0 dB gain on the output stage, which you can see on this meter here. And as more microphones are added into the mix, it's going to reduce the gain of all of those microphones to keep that nominal gain at 0. So because as you add more microphones in, they become additive or summed, and there's actually more gain in the mic mix scenario. Mariano asked, would the noise floor include HVAC? So typically, the mic mixer is going to happen after your input signal equalization, and actually after your AEC as well, that we haven't added in yet. So ideally, that HVAC noise has already been mostly handled by a high pass filter, a combination of a high pass filter as well as the AEC processing that we'll talk about later. So gating auto mixers are not auto mixers in general are not smart or intelligent. They're just very simple number machines that just look at what a signal is doing and react based on that very quickly. Um, so the and here's just an example of that that number of mics attenuation on the right. So we have a maximum number of 4 mics in this system. One is currently activated. You can see because there is a indicator at the top of each channel that tells you whether the gate has opened for that microphone. And as more mics are added into the system, we logarithmically attenuate that signal. So 2 mics equals 3 dB of attenuation. There are settings for this, the non-attenuation type, step, and maximum attenuation. All of that handles how that attenuation works. Richard asked, can you talk about what the depth does? Absolutely. So on the left-hand side here, so those non-attenuations all happen in this section on the right. On the left here, we actually have settings for the noise gate itself. These settings control the behavior of the noise gate. So the first one here, last mic on, this says that whatever microphone was the last one that activated, in this case, it would be microphone 3. Instead of closing the gate on it when that person stops talking, we leave the gate open, and that just allows a little bit of noise from the room to come through. A lot of times this can replace, the comfort noise that people like to add into systems. If you just leave one mic open on the mixer, that just helps overcome that. Then you don't need to add comfort noise because you already have comfort noise of what's actually happening in the room. Threshold level above noise is how loud that signal has to be before the gate will open. So by default, it's 10 dB over noise floor. The depth is how far that gate's allowed to close. So noise gates all have a closure setting that they're allowed to close to. By default, it's 60 dB. The reason for this is, and the maximum value that it can close is 60 dB. The reason for this is it's kind of an assumption that most signals are not going to pick up above negative 40 dB FS. Minus 60 is about where, whisper tones are happening. So anything above that is going to be where, normal sound is picked up or perceived by our ears. So 60 is just the maximum closure, how far we can slam that gate shut. If you have a really noisy system, that 60 dB might not be able to fully close that gate. If you turn it up to say like I only want to close the dB, but close the gate by 20 dB, that means that the gate will close, but it's not fully it's still allowing some noise to leak through. So the smaller the depth, the more noise you allow to leak through the system when all the gates are shut. So that hopefully that answers your question, Richard. The last one here, the hold time. So this is how long that once that gate opens, how long the gate must be held open before it's allowed to close. So there's a concept called ADSR, or attack, decay, sustain, release. The hold time is actually your sustain in the ADSR envelope. So attack is how fast the gate opens. Decay is how long is another factor that gates don't really use, but it's kind of a how long it takes to move to its holding level. Sustain is how long it holds there, and then release is how long it takes for the gate to close. So jumping forward. Oh, the last thing on this page is there's a mix gain, a post mix gain at the back on the far right hand side that allows you to just add and remove digital gain off the back of that signal. As we add more microphones to the system, that attenuation increases. So with 4 mics open, it's 6 dB of attenuation. This attenuation is currently in this system set to logarithmic. There is a linear setting where each mic attenuates again. Typically, the logarithmic is good enough. Someone asked, how is the noise floor dB established? It's a constant measurement, so it's looking at the open mics coming into the auto mixer, and it's just doing a measurement. It's if channel 1 is -60, channel 2 is -40, then the average noise floor would be -50. So it's again not an extremely intelligent, not crazy. There's no smarts, there's no AI to this. It's just doing math. Um, the other type of auto mixer that I'll go through real quick is the gain sharing auto mixer. So instead of a instead of closing gates around each signal when it's not being used, the gain sharing auto mixer applies gain to a signal to get it up to 0 when it sees signal coming in. So it actually modifies the gain that's applied to that microphone as it's being used. Instead of just closing a gate and leaving the gain alone and subtracting, it actually adds gain to the system. So this is based on an algorithm that was built by a guy called Dan Dugan. Dan Dugan still does sell his auto mixer. If you've ever used some of the older Yamaha consoles, they have Dan Dugan auto mixing built into them. Works basically the same way. So we have 8 microphones in this system. We're not measuring average noise floor. We're just looking at each microphone's actual noise floor. But the setup side of this open indicator just tells you how loud that signal has to be before the gain share opens and it starts applying signal to get it up to 0 dB. Depth is how far the applied gain is allowed to subtract out. Resting gain is the minimum gain applied to the signal. Threshold level is again another threshold for when it can start applying or subtracting gain out of that. And then you've got some ADSRs set here. So attack, hold, release. Again, there's no decay in these types of systems. And as microphones start talking or start being used, you can see that it brings, one person talks, it applies all of the available gain that's in that gain pool to the system, so to bring it up to as close to 0 dB as it can get. As more people talk, the less gain is available in the gain pool, so it gives less out. So this typically for when you would use a gain share versus when you would use a gate, Gating auto mixers are great for ceiling microphones or lots of microphones in a room. So like if you have a classroom participation system, so Tated mics or whatever at each student's desk, and they can push a button and they can start to talk, or you know they can just talk into the microphones and interrupt the professor. A gating auto mixer is really great for that because there's a lot of gain that you have to manage. If you have a couple microphones at a Q&A table or on a stage and you want to balance them and leave them all open, a gain share is better for this. The reason for that is a gain share doesn't require opening a gate, so you can kind of get more of that comfort noise. You can hear more participation, and it reacts a little bit differently. It reacts a little bit faster in some cases. So depending on what you need, you pick the one that you want. So putting that all together, we come back to that big signal flow that we have. We've got we've got all of our signal EQ put in. We've got our mic mixing put in. We didn't talk about these user program levels. Typically, these are going to happen. These are just for the program feeds in this case, because all of our signals are being automatically mixed. So we don't want the customer interfering with that. If in this type of scenario, if I needed user gain control over those gated mics, I would put that after the gating auto mixer and before the matrix mixer. So I would actually have a separate user program levels that went here, just so that I could modify that gating level. Or I would just use the post mix feed on the gating mixer itself so that I'm not creating more controls. Um, so the next thing we're going to talk about is dynamic processing. So it's not shown in here, but there's a couple other ways to automatically or intelligently process signals dynamically. So the first one is a compressor. This is another one of those that you may have seen in a studio or may have seen in live work. The way a compressor works is it attenuates signal based on how loud that signal is coming in. Really good for vocal performance, giving just leveling off extremely loud talkers. If you have a lot of people coming up to the same microphone, like a gooseneck, compressors are a really good way just to keep somebody from getting overeager on the mic. If somebody stands way off the mic and they're nice and quiet, that compressor's not going to affect them. And if somebody else gets way up on the mic, it will cut that off and level that back for you. The thing about compressors is they can't add gain to a system. Again, they're subtractive only. There is a makeup gain setting, but if you use this to try and add gain back into the system that wasn't there before the compressor, you will invert the operation of the compressor. It sounds really bad. It can get problematic very quickly. If you need to add gain to the system automatically, there is something called the automatic gain controller, or AGC. This helps out for both quiet talkers and loud talkers because it adds gain when you need it and it doesn't add gain when you don't need it. It will not lop off a loud talker in the way that a compressor will. So again, tools for specific uses. It also takes a little bit longer to kick in than a compressor or a gate. There's also a noise gate that you can just put in on its own. If you're using noise gates, just be aware of what you're feeding with it. Never put two gates in front of each other, which means don't put a noise gate in front of a gating auto mixer. The reason for this is the output of the gate will actually affect that relative noise floor for the gating auto mixer. So you're artificially changing your noise floor and lowering it. And then when that gate opens, it's going to snap the noise floor up. And now the auto mixer has to reevaluate and recalculate on the fly. So this will break your auto mixer very quickly. So now we've processed the system without our AEC and without our soft phone. Let's add in the AEC signals to the system. So we've got some other mics coming into the system here. They're going into our acoustic echo cancellation block, and then they're going into a gating auto mixer and going out to our soft phone. So again, set some terminology. When we talk about AEC, we talk about a couple things. Latency is how long it takes for the signal to make it from the left side of our AEC block to the right side of our AEC block. Any of you guys who play video games know latency. It's how long it takes for your finger to touch the joystick for the character in the game to move. So AEC requires look ahead time. A lot of these numbers, the latency numbers for these algorithms have actually changed. So the old algorithm was pre-version 6.0. And I don't think anything out there that we make still uses the old algorithm in any way. The new algorithm is actually not really the new algorithm. I think it's actually a little lower now. It's somewhere in the realm of 18 to 20. We've got a couple more milliseconds out of it because we have some really good guys in our audio processing department who built our AEC algorithm.
Gert
This is all
Rosenboom.
Sorry.
Gert Rosenboom is the
Oh
guy.
yes, Gert
Right. So,
Rosenboom, who is
but
one of the original Q-SYS guys, and he's on the Q-SYS periodic table of elements. If you're
absolutely.
in the experience center.
Hey, I
Um,
just want to throw out to our audience, if it, we, I think this was set up as a 1 hour, but it's probably going to go about an hour and a half. Thomas is getting into some really great details here, so we completely understand if you need to drop off. One of the great things is in the next day or two, you're going to get a recording of this. So if you need to drop off, feel free. If not, we're going to go ahead and we're just turning the corner on the AEC part of this. So probably another, I'd say 25 to 30 minutes to get through it accurately. But if you do need to drop off, we apologize for not advertising it in advance as a 90-minute, and you'll get a recording. So, but yeah, take it away. Keep going, Thomas. Great stuff, by the way. I love the deeper dive and the deep dive.
Absolutely. The current values for all of the latency are in our help documentation. If you look up AEC latency, it'll tell you exactly what these values are. um, as of today. The tail length. So when we look at AEC, what we're actually looking at is we're taking a time window of the room captured as is. And tail length is just how long that window is and how many of those reflections we can actually cancel. The maximum value is 400 milliseconds, the minimum value is 100, the default value is 200. And we chose the default value of 200 milliseconds because this is a nice middle value that gives you the maximum amount of processing while handling the largest number of use cases. This matches up with a lot of our partners, our ceiling mic manufacturers like Shure and Audio Technica and Sennheiser. A lot of them land around this 150 to 250 millisecond mark. And so that matches up really nicely with but this is the length of the adaptive FIR filter that we use to cancel those reflections. As you increase this tail length, you're consuming more DSP resources. AEC is one of the most consuming resources that we have in here inside of Q-SYS Designer. So as you increase that number, you're actually going to get less channels out of the AEC block. It will subtract for you inside of the properties window, but just be aware that 400 milliseconds is roughly half the channel count that the 200 millisecond value is. So if you have a particularly large room in your design stage, you're going to want to plan for that. Um, so the way that AEC works is that it uses this RMLR concept. So reference to microphone level ratio. And this is the difference between the reference signal, which is being fed into the AEC block. It's actually the last channel on the left, and the resulting signal coming out of this, and the resulting signal at the mics. So all of the other left channel signals. So what it does is the signal goes from the loudspeaker. So I'll actually start on the far right hand side here. Loudspeaker bounces off the wall, comes back to the microphone. This is picked up and it's measured by the AEC algorithm and compared with the reference value. And the reference value is what we're actually sending to the loudspeaker in the digital domain. Usually you want this as close to the actual output the flex out or the digital amp signal if you're using a Q-SYS enabled amplifier like the CXQ or the SPAQ. You want this as close to the speaker as possible so that you get the most accurate reference to compare to. We compare both of these and we get this reference to microphone level ratio. It's always a ratio because it's a comparison of two signals. Um, and the difference between those is our echo return loss. So it's how much we have to get, how much we have to subtract out of the AEC to cancel out or remove that extra signal that's reflecting around the room. So a couple other pieces of terminology. Residual echo suppression, or RES. This is usually in most of our competitors who do AEC. This is a button or a off, low, medium, high. We have a percent value. It's all the same. This is the magic sauce that we all bake into our AEC processing to do nonlinear processing and remove the error correction that happens after the acoustic echo cancellation. After we cancel out that signal, this is the extra sauce you put in to make it sound good again. Voice lift. So voice lift is taking the microphones that are in the room and putting them out of the same speakers that are in the room. Mix minus is strategically mixing through your crosspoint mixer, strategically mixing those voice lift microphones so that they do not come out of the nearest speakers, or they're just strategically mixed. Anything that where you're taking the microphones in the room and you're mixing them to speakers that are also in the room constitutes mix minus. Typically, we recommend against it unless you need it, because at making a mix minus system with gets to be very complicated, especially when you combine it with conferencing, which wants really stable audio. As you start to introduce more of that voice reinforcement, you get you're more likely to introduce feedback. You're more likely to introduce issues with your conferencing outputs. We do have pins on the AEC block called the reinforcement outputs. Just be aware that the way the reinforcement outputs work is different than you might think. So the reinforcement outputs to do the entire AEC process, but they skip the residual echo suppression. So they don't do that magic processing. So they still have the same latency on them and they still go through the AEC block. They just don't have some of the cleanup signals at the back end. Typically, those reinforcement outputs are to send to other places. So like auxiliary spaces, places not inside the room. If you're doing voice lift, there are other ways to accomplish that we don't cover in this specific PowerPoint. So typically put the AEC block closest to the inputs because we want to hear what's naturally coming in from those microphones in the room. So when you're adding AEC, the process is add your mic block, add your AEC block, add your EQ processing. So here we've placed them inside of a channel group. We placed our high pass, our parametric, our low pass, and our compressor inside of our channel group. And then we fed that out to the gating auto mixer, which then is going out to our soft phone. Again, don't put any dynamic objects in front of a gate or in front of the AEC, because for the same reasons that we don't want to manipulate the signal going into a gating auto mixer, we don't want to manipulate the signal in front of the AEC either. Some people will put the high pass filter in front of the AEC block to clean up the signal going into the AEC. I personally don't, and the best practices guide here doesn't show you doing that, but I have seen people do it. Again, most important thing is having the closest to natural sound coming into the AEC block and having that reference signal be as close to what is exactly going out of the speakers. When you're not using voice lift, if it goes to the speakers, it goes to the reference signal. The reason that we have this exception for when there is no voice lift is because When you're doing voice lift, you have to strategically mix those so that the speaker that is closest to that person talking doesn't include the microphone that is closest to that person talking, because if you send their voice out of that speaker, it's going to confuse the AEC block because it's looking for their speech pattern and it will cancel it out of that speaker. Somebody asked, do you want separate EQ for far end and for voice lift? Yes, you do. So typically I put almost no EQ going to the far end audio. So I want to leave it as natural as possible. If I need to EQ it to make it sound a little better, that can be more color tone. Going to the far end, you're tweaking it for a playback system. On the other end, you can also compress it a little more because it's going to get compressed anyway. Generally speaking, I don't do much of anything to go to the far end. We also don't do much of anything here. In fact, you can see that this one does absolutely no post-mix EQ. For voice lift, I will definitely do different EQ. I won't necessarily separate the pre-mix EQ out for them because the microphone's a microphone and I want it to sound the same, but the voice lift's going to get some different EQ because you're going to EQ the speakers itself. Is the reference level the same level that is going to the speakers? Yes, it is the controlled volume level. So yeah, you want it after your user gain that is controlling the master volume of the speakers. The reason being, if you adjust the volume of the speakers and you don't adjust the reference, you've now modified your RMLR ratio because now the speaker level is louder than the mics coming in, but the mics are still listening to the speakers. So you're just modifying it. So again, I typically put the reference on the same pin that is going to the speakers. I will usually put this after the EQ. Some people put it before the EQ. Your mileage may vary. Again, never put a mic signal into its own reference. This results in a dual cancellation. You're canceling the signal coming from the speakers and from the person talking because those are summing together because they're basically the same frequencies, and those frequencies add together when they're being converted to in the ADC. So this typically results in if you've ever heard somebody sound like the Little Mermaid or you start to sound like a robot, typically this is dual cancellation. But we've got all that set up. Now, assuming we've set all of our microphones to minus 20 dB nominal, we've got our 15 dB SNR for intelligibility. Now we've got to set the amplifiers. So set the amplifiers to the maximum, to the minimum level, or you set the RMS level on the output block, your line outs, if you're just going out to an analog amp, or the RMS values if you're using a Q-SYS amp. And then you use your preamp gain to bring all those program sources to minus 20, leave your program sources at unity gain, and with a calibrated program source like white noise or pink noise, you bring up the amplifier until you get to that comfortable listening level, typically between 70 and 85 dB SPL. 85 is the conversational standard. It also happens to be the typical standard for jazz. Is 85, rock's usually 95 to 105. That number's been creeping up over the decades because the loudness wars. And then you make a test call. So always, as part of your commissioning process for AEC and conferencing, always make a test call. You cannot tune a system that you can't hear. So even if you just go down, you turn the system on, you go down the hall, that's typically measured at ear level. So you want that. If you're in a conference room, typically people are sitting down. I would measure it at ear level. If I have I don't know, if I'm doing a conferencing system for a fitness studio, maybe I would do it at standing level. But typically 4 feet, seated position. But yeah, always make a test call, adjust your open up your AEC block while you're in the test call. So this is what the AEC block looks like. In the bottom right is your noise reduction. This is that cancel out HVAC noise, the building rumbling. This is static, steady noise. So this is stuff that's always going to be there or is there for long periods of time. Noise reduction's not magic. It's an on or off with 6 to 20 dB. Of noise reduction that you can add there. It will, if you have a lot of it in there, it will change what it sounds like. RMLR. So this is that reference, that ratio, that reference to microphone level ratio we were talking about. This is that shown visually. So ideally, you want it dead center. And in fact, the chart is this meter color codes itself based on how you've got all of that configured. So as you adjust that reference gain on the bottom, you will actually move that reference, that RMLR meter around. You want it at 0 dB, which is why this meter here shows target 0, is you're trying to get this number to read 0 if you can. Get it as close as possible. Typically, if I'm within 1 dB, I'm usually listening or talking to somebody on the far end to hear how the room sounds. If they like it a little bit higher, it can go a little bit higher. It can go a little bit lower. Do what sounds good or do what, reduces the echo the most. Up in the top right, we have an adaptive filter. Only use this if you are muting mics in front of the AEC block. So if you have Deus mics that have a push to talk, you're using the adaptive filter. If you're using a ceiling mic that you're never muting, this stays at -100. What this does is it pauses when that microphone gets muted and the level drops below a certain value. It's like a reverse noise gate, and it actually pauses the convergence and adds noise into the AEC to hold it there. So typically, if you need to use this, you set it a few dB below the noise floor when it's unmuted. So if you're going to configure it for a push to talk, you push that PTT in and you look at on a meter inside of Q-SYS to see what that value is when nobody is talking, and you set it just below that. So when they release that, you see the value drop and it puts that noise in for you. Again, only use that if you're muting mics in front of the AEC block. Next, we have our RES enable and our RES value, RES intensity. So again, as you increase this, it's going to introduce more error handling into the system. It's going to put more of that nonlinear processing in. You will approach half duplex, which is half duplex is cancellation. So as you increase that value, you're going to introduce the likelihood that you are introducing a double talk condition. So basically half duplex is you'll start to hear your voice again going to the far end. So just adjusting this as you're talking, make sure that other person is communicating with you about what they hear. Personally, I like to be on the far end when I'm setting AEC up because then I can hear exactly what changes I'm making and how I'm impacting the system. It's just a little bit easier than getting someone from your office on the far end and then asking them for constructive feedback. It's helpful, but I like to be the person on the far end. So I'll put the customer in the room. I'll ask them to talk for a little bit and I'll walk down the hall with my laptop. If there's still significant echo, check your signal chain to make sure you're not misrouting or looping anything, or accidentally sending a signal to the reference that shouldn't be going there. Mute individual microphones. So the rule of elimination. So mute microphones until you identify the one that is problematic, and then address that one specifically. If you get all the way through that and you still have significant echo, that's when you check your tail length. So tail length is usually the last thing I check because it's the one that's most likely to mess with your entire design flow. Um, a lot of systems these days are designed kind of at the bleeding edge of what the AEC channel count can do. You'll stack 8 channels on a core nano at 200 milliseconds, and because that's what it says on the specs on the website, is it says 8 channels at 200 milliseconds, and the design engineer sees 8 channels of AEC. And then you get into that room and you find, oh shoot, I need 300 milliseconds of tail length. Well, I've lost 2 to 4 channels now. Um, that's a problem, and you can't just add another Q-SYS core um, to get more channels. You have to step up your Q-SYS core. We I have talked with Gert and Kevin Rodas. Actually, the three of us have kind of gone back and forth a little bit about whether you can use another Q-SYS core to increase your total number of AEC. Um, QLAN is fixed at 1 millisecond, so technically yes, but any travel time between the microphone and Q-SYS and the AEC block gets stripped off of your tail length. So if it takes 5 milliseconds for that mic signal to get from the microphone to the actual AEC block that it's using with the correct reference signal, instead of 200 milliseconds, you'd be at 195. So it's just reducing how much of that echo you can cut out. This is also a thing with ceiling microphones. Some of them have additional latency, so you may want to introduce a delay in that microphone signal so that to time align it with the signals that are inside of Q-SYS. Just be aware of that. And then repeat that test call for each AEC block and each conferencing type. If you are using a system with multiple, so say you have a Zoom room or a Teams room, like a UC compute inside of your room, but you also have a VoIP extension system. If the two have the ability to be merged, test it with them merged, because that will change things. And then after that mix, after you've gone through all of that, make sure to put EQ, user level controls, and limiting and delay on your amplifier outputs to make sure that those are set up properly. Use the manufacturer recommended curves if you're using non-Q-SYS speakers. If you're using Q-SYS speakers, we have voicing blocks inside of Q-SYS that use what we call intrinsic correction. Um, uh, and this accounts for the imperfections of the frequency response of the speaker. Typically, you want that parametric, that EQ that's on the output chain, only to be used to account for the response of the room and reflectivity of the room. Don't use output EQ to handle feedback, because again, you're applying it not just to the microphone that's feeding back, but to every signal. And Anonymous asked, should any signal processing in the microphones go before or after AEC? Always after the AEC block. Again, the exception sometimes is some people put a high pass filter in front of the AEC. I don't, and our best practices say not to. So everything after the AEC block, you want to hear AEC wants to hear what's actually happening in the room. So user gain controls, typically the less is more. If you don't have to give the user control, don't give it to them. The best way to ruin the room is to let people make adjustments to the room and then forget that they made those adjustments. Maybe they're using the room for voice lift only. They increase the gain to all of these outputs. Then you get into a conference call and you find that the room is way too loud now, and it's more likely to feedback. Also, adjust the gain properties for those user gain controls. This system, this example here shown, has the max gain set to 0 and the minimum gain set to -40. I typically will do plus or minus 6 dB, maybe plus or minus 12 if it's a particularly live system that needs a lot of headroom, but I don't give them a lot of room to make that room louder or softer, because you'll find that one person really likes the room super quiet and then nobody can hear anything if they've moved it minus 40 dB. That's going to make the room really quiet. So that just use common sense here. Don't give them enough room to destroy the gain structure of the system. And then on the output side, we have another piece of dynamic processing. This is called a peak limiter. So a peak limiter, what it does is it's like a compressor. If a signal gets too loud, it levels it off. But instead of a compressor levels it off on a ratio curve, uh, on a logarithmic curve, a limiter lops it off. So the peak limiter in Q-SYS works similar to if you've ever heard of a brick wall limiter, where basically you run up to the signal and it just lops it off. So anything that exceeds that gets cut off and folded back. This sounds very noticeable. So if you have it set too far down, the threshold set too low, uh, you will hear crunch and distortion. Um, the default threshold is 0. Typically, you set it a couple dB below what your clipping point of your amplifier is, or the clipping point of the speaker, whichever is lower. So you can see here, this triangle represents signal that has exceeded the limiter, and we are cutting our applied gain by 6 dB. So that's showing you how the limiter works. Typically, if I know that the signal clips for Q-SYS and for the line outputs, clipping happens at 0. So I typically just set it at minus 3 dB. So the limiter kicks in just before that signal is going to clip on the output. If you're using a QLAN enabled amplifier, we have protection limiters built in, so you don't really have to do this. If the speaker blocks are configured properly. There's a couple different types. DAC limiting is peak limiting we just showed, so it's clipping at the gain stage going into the amp. Protection is thermal clipping, so this is looking at the transformers and transistors inside of the amplifier, and if they get too hot, it will put them into thermal protection. And then we have compute limiting. So if for whatever reason the load type is straining the DSP inside of the amplifier too much, then we may limit that signal as well. And then on your outputs, we just want to make sure that we're gain staging the outputs properly as well. So there's RMS output levels for all of the line outs. It's shown here. So by default, it's set to plus 21. So just look and see what you're sending that signal to. If you are sending it to a professional amplifier, that we all use a commercial amplifier, this is perfectly fine. But if you need to send it to a consumer level device, maybe someone brought a Zoom recorder, then you need to match that sensitivity. +4 is great. -8 is good for consumer level stuff. There is a chart here. So +24 is our professional line level. Consumer line level is -10 dBV, which means you have to convert that to dBu. And then mic level, if you're sending it to that Zoom recorder that has a microphone input, you want to set this to -40 dBu. Just make sure that you're not blowing up the gain staging of the device you're connecting to. And this also applies to press box inputs. If you're sending these signals to something like a press box, I would just set it to microphone, or either microphone or professional level. Just work with your customer to make sure that they know what people are expecting to connect to. Maybe label it with what that output level is. So just as a quick recap, please set your gain staging. This is the fix. This is the magic bullet for all of your DSP problems, is gain staging. Starting from there at the closest to the source gives you the best odds of success, and it makes solving other problems downstream so much easier. Microphone EQ, put EQ on every channel, on every microphone channel. and use it. Actually go through and trim and set those EQ parameters. How many times I come into a system to help troubleshoot and I see that all of the high pass and low pass are set to default, and the parametric is absolutely flat for 20 mics that are wide open in a room. They're set to push to mute and they're on gain sharing, and there's no frequency adjustment there, and the room is feeding back like crazy. It's like super simple fix. Um, use dynamics when necessary. So automatic gain controls, compressors. When you need to tame that system a little bit, throw some compressors in there. Um, use auto mixers. Don't place gates or level controls in front of the auto mixer, and give the user the fewest tools to break the system. So just be cognizant of it. I know we can't avoid it entirely, but just don't give them enough room to blow up your gain structure that you worked really hard to set. And then finally, just make sure that you're setting up that output limiting, and you're calibrating those outputs for the proper destination devices. All right, I think we made it in about 90 minutes. So if you need to jump, thank you very much for attending. Me and Dan are gonna hang out for a few minutes and try and answer some questions. But thank you guys for coming out, and you should see the recording up in a couple days. Um, let's see, stop share. So
Cool.
there we go.
Oh, we got a couple
Yeah.
questions. Where are they?
What would be the best practice for dealing with AEC in a room with voice lift where the microphone moves around the room? So that's a great question. So I think typically
Cardioid
this is
element.
sorry.
There's some things I want to consider. A cardioid element would be a good start, or
Yeah, so I typically assume in a scenario where the microphone's moving around the room, I'm typically assuming this is like a handheld or a lav mic moving across the stage. So what I would say for that is if you're using a ceiling system, you're not doing a mix minus there. So that's thrown out the window. You can't mix minus this unless you have the ability to, put the invisible fence up on the presenters so that they cannot leave the stage. Um, Tune the room for where that microphone is supposed to be. Um, you're not going to be able to solve for every position that that person goes to. So just tune the room as best as you can. If you have the ability to tune it, if it's a full ceiling system all the way around and you don't have a stage area, then make sure to ring that mic out with the speakers as best as possible. So that's going to mean walking around the room with that notch feedback controller and inducing feedback, talking loudly, talking softly. Maybe if you're maybe a little bit height challenged, or height impaired, maybe you're lifting the microphone up and increasing that gain so that you're introducing the likelihood of feedback into the microphone. Drive that noise notch feedback controller, or use your ears and just try and squelch those frequencies as much as possible so that that voice lift um, is broken down and tuned correctly. Aside from that, the AEC is going to react to what's happening in the room. So if there's a lot of if there's a lot of voice coming into the room, the AEC, you may want to exclude that microphone from the AEC entirely and just blend it into the conferencing system manually. It really depends on how that room is constructed, and if you have a specific scenario, you're welcome to email your Q-SYS AET. If it's me, shoot me an email. If it's not me, if it's Michael Perry or Jim Barry, and I did just pick the two guys who rhyme. Talk to your local Q-SYS applications engineer about that scenario, and they'll be able to give you exact detailed advice for how to handle that.
This one there'll be an exam link that goes out, David. The question is, the class is supposed to provide CDS credit. There should be an exam link when you that goes out with this, and you just click that exam, go take a quick 10 questions, and then you'll get a certificate sent to you. So Perfect. All right.
Oh, and then yeah, Aaron Darnell helpfully posted. I know this was many minutes ago, but Aaron posted a link to the Yamaha Sound Reinforcement Handbook. That that would yeah, Google it. It's been around forever. It's a great resource for learning more about live sound and more about the electrical engineering behind live sound as well, because I like to call live sound the most subjective objective science, because it's an objective science, but everybody's got an opinion about how they like it. Um,
Yeah, I like that. That's true. But there is some science involved in it. So,
there's a lot of science.
yeah. So,
Let's see.
well, cool. Well, we'll let everybody go.
Yeah, I think we're gonna go ahead and call it. So thank you guys for
Yeah.
coming, and have a great day.
All right. Thank you, guys. Later.